Alright, so here we will look at another example of how to use torques in rotational motion problems. Basically, this problem is going to illustrate our Newton's second law for rotations. Okay, let's begin. We have a thin uniform rod. Thin means its thickness is negligible, and uniform means the mass is distributed evenly throughout this cayenne colored rod. And on the rod we have four different forces acting in different directions as shown. Our ultimate goal is to find the angular acceleration alpha for the rod. Now, given that the length of the rod is 0.7 meters and mass of the rod is 1.6 kilograms. Since the rod is uniform and the mass is evenly distributed, we add a fifth force, which is the weight acting through the center of mass. This is 1.6 times gravity, g. Now our free body diagram is complete, and we indicate that any counterclockwise torque is positive. Alright? Now let us remember what the second law for rotation was. For rotation, the second law was written as summation of all the torques on an object is equal to its moment of inertia times its angular acceleration. Therefore, to find what alpha is, we need to determine the inertia, moment of inertia, and all the torques produced by all these different forces acting on the rod. Let's begin by summing up all the torques. Individually, let us investigate all of the different forces. Let's look at 10. Before we do that, let us also note that there is a fixed pivot that this rod is fixed to. This pivoting point X is at the left end of the rod, alright, and it is fixed at that point, and all these forces will try to rotate this rod with respect to this fixed axis. Okay, alright, so about X, what is the torque produced by the 10 Newton force? Well, it is simply 0 Newton meters. Why? Because as you can see, it is directly at the point which is fixed. The force is applied at the fixed point. And remember how torque is defined. Torque is the magnitude of the force times the distance from the force application point to the fixed pivot R, and times sine of the angle between F and R. Then here R is 0. There is no distance between the force application point to the fixed pivot. Hence the torque is 0. Similarly, for 60 Newton force, which is a horizontal force, we see that the torque, actually this is not summation of the torque, this is just the torque due to 10 Newton force. The torque due to 60 Newton force is also 0. But in this case, the reason is a little bit different. 60 Newton force is a horizontal force, and here we have the fixed axis right here, right? Horizontal force means that the theta is equal to 0 because the force is parallel to the fixed pivot. It's like if you have the door, if this cayenne colored rod is your door and this is the hinge of the door, if you try to pull along the length of the door will never open because no torque will be created. Hence, the torque produced by 60 Newton is also 0, but now it's because theta is 0. Alright, but all other forces actually produce torque. Let's see how. For the 7 Newton force, it is a perpendicular force, therefore it will produce maximum amount of torque. And about the fixed pivot X, what is the torque due to 7 Newton? It is the size of the force, which is 7, times the distance from the fixed pivot to the force, which is the length of the rod, the total length of the rod, which is given to us as 0.7 meters. So 7 times 0.7 sine of theta, and theta is 90 degrees because it is perpendicular the force is perpendicular to this blue line joining the pivot to the force. The angle between them is 90 degrees. Hence this is 1, but remember we chose counterclockwise to be positive. This 7 Newton force acting vertically downward would try to rotate the beam this way, which is a clockwise motion. Hence we need to include a negative sign here. This torque is of the size of negative 4.9 Newton meters. Okay, then let's move on to the next force. The next force is the weight. Okay, the weight is 1.6 g. What is the torque due to that? It is the force times the distance from the force, which is half of 0.7, right? Hence the torque produced by the weight, let's just call it W here, is again negative because this weight will try to rotate the beam in a clockwise direction. Negative the size of the force, which is 1.6 times 9.8 times the distance, which is 0.7 over 2 times sine of, again this is 90 degrees as can be clearly seen from the diagram. Alright, this comes out to be negative 5.5 Newton meters. To that we have one force left, which is the 9 Newton force. Now before we get into the basic calculation involving the 9 Newton force, let us remind ourselves and look at torque, the definition of torque, a little bit more closely. Torque is defined to be F times R sine theta, and we know what F and R stand for by now. And F, we can rearrange this definition and put the sine theta here beside F, and then put it in parentheses and say that it is being multiplied with R. These two expressions are the same thing, torque, right? However, now this parentheses expression here looks a hell lot like a component of a force, right? It is actually a component of a force. So a simpler way to think about torque would be if you have a beam or anything actually, and there is a fixed pivot about which you're making the thing rotate, and a force, say F, is being applied at an angle theta like so, then the force must have two components, right? The x and y components. Now the x component, the horizontal component, is parallel to my fixed pivot point, right? It is basically, you can think of this as a hinge and this as a door. Applying an x component of the force just means that you're pulling along the line of this beam, which wouldn't cause any torque. So we can completely ignore this horizontal component, and it turns out this vertical component, or the perpendicular component to the pivot axis, is F sine theta. Okay, so any force that is, so the moral of this story is any force that is at an angle to a beam or anything that you're trying to rotate, the only contributing component of that force which causes any torque that you need to worry about is its perpendicular component. Alright, the component perpendicular to the line joining the pivot point to the force. Hence, we can only think about, for any of these angular forces, we can only think of their vertical components. Okay, makes our lives a lot simpler. So if you think about this 9 Newton force, you know that this 9 Newton force will have a y component going like that and an x component going like that. The x component is, you can see clearly, parallel to the beam, so will not cause any torque. Hence the only component we worry about is this vertical component, and since this is 30 and this hypotenuse is 9 newtons, we can simply say that this is 9 sine 30, and this is the only force we worry about. Hence the torque by the 9 Newton force is equal to F sine theta, which is 9 sine 30, times the distance from the pivot point to the applied force, which is 9 newtons, right? This is applied, 9 Newton force is applied at the center of mass, hence the distance is 0.7 over 2. Okay? So this gives me a torque of 1.58 Newton meters, and it is a positive torque because this is an upward force, a vertically upward directed force. So about x, this will try to cause a rotation of the beam in a counterclockwise direction, hence positive. Alright, now it's time to sum up all the torques that we have found. Therefore, if we sum up all the torques, we are left with torque due to 10 was 0, torque due to 16 was 0, torque due to 7 was negative 4.9, torque due to the weight of the bar was negative 5.5, and torque due to the 9 Newton force was positive 1.58. This gives me a total net torque on the beam to be negative 8.8 Newton meters. A fun fact here, Newton meters is, if you would think about it, is the same unit as work. Work was defined to be force times distance. This is also unit, this unit also signifies force times distance. However, torque is a completely different thing than work. Even though its units are the same, torque you cannot write as joules, okay? Torque's unit is just Newton meters. It's a funny little conundrum in physics. Anyways, now let's move on to the next goal of the problem. What is the next goal? To find what this moment of inertia is for the beam. Now from the table we can find that I of a uniform thin rod about its center of mass is 1 over 12 its mass times its length squared. If this was a rod, then about its center of mass, the moment of inertia has already been calculated to be 1 over 12 ml squared. However, our rotation axis is not the center of mass, rather it's at one end of the rod. So we would need to use parallel axis theorem to find our moment of inertia about that fixed axis. So this is our axis x, right? And we need to use parallel axis theorem, which states that I about that axis x that we are choosing is equal to the center of mass I meaning moment of inertia, plus m, the mass of the beam or the rod, times the distance between the two axes squared. So therefore, moment of inertia about the center of mass for this rod is 112 m L squared plus the mass times distance squared. What is the distance? This is one end of the rod to the center of mass, so the distance is half of the total length. So L over 2 squared. Then if like we have done so in a previous lecture video, this comes out to be 1/3 ml squared, and we know the mass and length of the beam. So 1/3 mass is 1.6 kilograms times length was 0.7 squared. This gives me the moment of inertia of this beam around our chosen axis, that is x, is 0.261 kilogram meters squared. So we have found two things. We have found the torque, the sum of the torques, and the moment of inertia of this problem. Now it's basically putting all these together. Putting I, alpha, equal to summation of all the torques, basically just filling up this equation right here, Newton's second law for rotations. We want to find alpha, so alpha is just dividing both sides by I, gives me torque, summation of all the torques over I. Summation of all the torques is negative 8.8 Newton meters over I is kilograms meter squared is the units, and its value is 0.261. Alright, one of the meters can go away, and basically if you do this calculation we end up with negative 33.8, and the unit ends up being radians per second squared. So this, if you manipulate newtons per kilogram meter, this unit is actually becomes radians per second squared. Alright, so this is how you use Newton's second law for rotations.